Hi, welcome to Mechanics Transvariance. Transvariance is the first paper of Mechanics, and this is the fourth video of Transvariance where we're going to discuss other transvariances and we're going to look at other simulations in the simulator. Okay, the next video, I'm just going to talk about the next video for a second. No, I'm going to talk about the next video at the end of this video. Okay, so let's bring in the simulator. This is the new version. I fixed a bug in it, and I also added a pause button. So to prove that this thing works as it did before, I'm going to run the standard Michelson-Morley. All the transvariances are turned on. Okay, and it works just like it did before. 21.5 seconds is the time. Okay, so what I'm going to show you are other simulations we have in there. You've seen all the Michelson-Morley. Trains are just experimenting with the train. That's just kind of like the debug work for this. So when I release the software, you can go look at these on your own. The emitter we saw last time, and then waveguide. This is interesting. I decided we need to understand why this occurs in the Michelson-Morley. Let me show you what I mean. So if I go to Michelson-Morley and I take off wide beam, or I take off narrow beam rather, you see how the reflected wave goes up at an angle, and then it reflects at an angle, where this one reflected parallel to the wall. And I wanted to explore that to see if that was another transvariance. So what I did is I came up with a waveguide. I'm going to show you the corporate one because this got too complicated. So what we have is a whole bunch of reflectors. Now what I should have done is made these green walls non-reflective, because they end up making all these other little reflections in there just come in. And also set this up so every time something reflects, the reflected element has less intensity, to try to get a feel for, you know, how much loss anything, how much, like you can tell this reflected more times than this guy over here, to see what the components are of the wave that is emitted from the waveguide. Okay, but the problem is there's so many reflected crap in here that when you watch the return signal, you can't tell what's the return signal from the emitted signal, from the crap that's floating around. So I came up with a simpler version. Okay, now as the wavefronts come up, you see how they're parallel? They're in line with each other, and they're parallel, attacking the wall. And what we're going to do with the pause button here, okay, so the two leading edges line up on the emitter at exactly 24 seconds. Okay, now we're going to put this simulation in motion. See, they're coming off at an angle right now. Same here, and these angles line up. And I think that's necessary because when they're emitted, they have a Doppler shift from the source. They have to have a Doppler shift from the source. Okay, so I only have a resolution here of a tenth of a time unit. Okay, and so that rounds up to there. So this is, you know, calculated from the time dilation equation, but essentially because of rounding error, let's say it's exactly 24. Okay, if I had ability to stop this at smaller increments, I could probably get this right on. But it shows you that even in the observer moving with the range detector here, they're going to measure the same range to target as if even if they weren't moving, which shows that the transvariances work to give the illusion that the experiment is standing still. So there is one Achilles heel here, though. And let me do this again. So the wall up here is not reflecting all the energy at the same time as it was in the stationary case. So that may be a way to make a detector that we're in motion. Okay, this cannot be done any other way, otherwise you get the wrong answer down here. This has to be correct. This slanting of the emitted signal has to be correct. Otherwise, you would get the wrong answer for the range to target. Now let me show you another waveguide, a parabolic dish, stationary. And again, the wavefronts go off nice and parallel. They reflect nice and parallel. Okay, you see how the reflected energy just centers right around the source, which shows that everything arrived in the right order at the right place. And the round trip time was 18 time units. So now let's show this again with the parabolic dish in motion. And again, we get our slanted wavefronts. Okay, that has to be. I can't come up with a reason why any other way would work. Okay, and you can see the source energy or the return energy centers around the emitter again. And the answer again is 18 time units in the time frame of the radar unit, the parabolic dish. Okay, which says this is correct. There's no other compensations needed to get the correct answers. Okay, but again, when these wavefronts hit the wall, they hit them at an angle. And so that's part of the Achilles heel. Like I said in the previous videos, in the introduction, the gift has to have an Achilles heel, otherwise it would violate locality. Okay, so there are other simulations in here as well, a distinti interferometer. This is just where I'm trying to send another pulse around. That didn't really go anywhere. Then there's a simulation for the clock, just to double check Einstein's clock and doing it in motion. That kind of thing. This thing goes for 10 pulses, or sorry, for 7 pulses before it stops. I'm not going to put you through all of that. What is this? Yeah, these are just other little experiments I was working on to demonstrate stuff for videos and whatnot. Anyway, we're done with this demonstrating the simulation. There's other items in here, that you can try out. If you want to just check these out. And they're good examples of how to write the simulations for this. Okay, so let me stop this. Okay, so in the next video, we're going to cover the Achilles heel of the gift, the things that we could capitalize on to make instruments and devices to detect things that people have never been able to detect before. Okay, because the nature's gift, the gift has to have an Achilles heel. Okay, and I'm going to show you a lot more of them that scientists are just totally oblivious to. And it's so easy, even a physicist can do it. But what I'm going to do is, this is new material that's not in the paper. I'm going to make this for Patreon members only, passenger and above. Okay, so you're not. So the rest of the world isn't going to see 105 unless you become a Patreon member. And for 106 here, I'm going to make that available to everybody so you can see how easy it is. We're going to do an example of how to add your own simulation to the software, and give a general overview of what's in the software, how to find stuff, yada, yada, yada. Okay, so if you're new and you've never seen my stuff before, this is all new to you. Okay, my website's at www.distinti.com. My Patreon site can be found by clicking this link. Our blog site can be found at this link. All the papers for ethereal mechanics that have been published are underneath this link, and they're all listed, and they're in subgroups. If you need to know why this is important, there's things here that are more important than climate change that are there. We have basically all of our eggs in one basket. Okay, this world is one atomic war, one asteroid impact, one supervolcano away from starting over from beginning, if not altogether total extinction. Okay, and I think our worst threat to us is ourselves. Okay, so with that said, these are just the links again if you just want to go there separately and type these things in. I think these links are in the low bar as well. Thank you. No more voodoo physics.